So in the last section, we looked at the Taylor polynomials and how they provided a linear approximation of our value of our function at a certain point. While that's a good approximation, we can actually do better by expanding our understanding to the Taylor series. And the Taylor series, and especially the Maclaurin series, are special series that involve the derivatives of functions. So for example, f of x can be approximated using the initial value, and we're going to use centered at 0 for now, along with our first derivatives, and then expanding out to include higher powers. And if you notice the pattern here, it's just like we were expecting. We have an x cubed here with the third derivative and a 3 factorial in the denominator. We can go to the fourth derivative and x to the fourth, and so on, to include as many terms as we like to the nth derivative, again centered at 0, n factorial x to the n. And this represents the Taylor polynomial for x number of units. Now this is a special series being centered at 0. This is called a Maclaurin series. The Taylor series is not just centered at 0, it can be centered at other points as well. If we wanted to look at f of x centered at a point A, we could do that. It's the same thing, now just centered at A, but now when we do that, we have to make this adjustment, x minus A, as our variable. So again, second derivative at A over this 2 factorial x minus A squared. And if we just continue that pattern, we can continue that out until we've decided we've had enough units or enough terms in our polynomial. That should be an n, x to the n power. And that's the definition of our Taylor series, and centered at 0, that's our Maclaurin series. So let's do an example here. We're going to find the Taylor series centered at x equals 0 for f of x, which is 1 over x plus 2. And so the first thing we want to do is we want to start finding these derivatives. Now, I recognize that this is x plus 2 to the negative 1 power. That's actually pretty helpful. So when we start working these out, we want to start with f of 0 first. So a 0 put in there gives us 1/2. And if I go f of x is equal to, well, f prime of x now is, by the power rule, we have a negative 1 to the negative 2 power. And if we use the chain rule, there's nothing really that happens there. And we just continue this pattern. Negative 2 comes down to the negative 1. That gives us 2x plus 2 to the negative 3 power. And so on. We get the negative 6 to the negative 4th power. And let's do one more. We're going to go to the fourth derivative for this. So negative 6 times negative 4 is 24. X plus 2 to the negative 5th. Now let's find these at our center point, which is 0. F prime of 0, we'll put a 0 in here. We're going to get 2 to the negative 2 power, but we also have a negative 1, or negative 1 in front there, so that's negative 1/4. F prime at 0, well, that's, again, 2 to the negative 3 power, that's 1/8. We also have a 2, so 2 times 1/8 is a positive 1/4. F prime of 3, or F prime of 0, triple prime, we have, again, 2 to the negative 4, that's 1 over 16, times a negative 6. So negative 6 times 1 over 16 would actually give us negative 3/8. The fourth derivative, Well, that's 2 to the negative fifth power. It's 1 over 32 times 24. So 24 over 32 is going to give us 3/4. And we could probably stop there. So when we do this, we're going to get f of x. Let's put it into our structure of our Taylor series. And we're going to see f of 0, that's 1/2, plus f prime of 0 times x. So that's 1/4 x. A negative 1/4 x plus f prime of 0, which is 1/4. But we also have that 1 over 2 factorial there, x squared, plus we have negative 3/8, that's our third prime at 0, times the 1 over 3 factorial times x cubed. And one more, we get 3/4 times 1 over 4 factorial x to the 4th. Now, if we work this out, we're going to get 1/2 minus 1/4 x. This is 2, so we're going to get 1/8 x squared. This is 3 factorial is 6. 6 and a 3, that'll give us 2 and a 1 there. And that's negative 1/16 x cubed plus, 4 factorial is 24. Let's make that 8 with a 1 there. That gives you 1 over 32 x to the 4th. And that is our Taylor series that approximates 1 over x plus 2 centered at 0. So what happens if we're not centered at 0? Let's look at this example where we get f of x is equal to sine 3 of x, and we're at x equals pi over 6. Well, just like before, we need to find f of 0 first. And so sine of 3 times 0 is 0, which the sine of 0 is 0. I always start with the derivatives. That's sometimes the easiest part for me. So f prime of x is 3 cosine 3x by the chain rule. F double prime gives us another 3 coming out here. The derivative of cosine is negative sine, so we'll get negative 9 sine of 3x. F third derivative of f of x is 3 times negative 9 is negative 27 cosine of 3x. And our fourth derivative is going to give us, well, the derivative of cosine again is negative sine. We have a negative sign already out here, so that's 81 because of the 3. So that's 81 sine of 3x, and it is positive. All right, so now f prime of 0, what's 3 times cosine of 3 times pi of x. And I just realized that I have a pi of x over here that I need to fix. So our first value is actually pi over 2. That should be pi over 6. And sine of pi over 2 is 1. So sorry about that. We're going to fix that. So 3 times cosine of pi over 2 gives us 3 times, this is 0, so that's 0. F double prime of 0 is negative 9 times the sine of pi over 2, which we already learned is 1, so that gives us a negative 9. Should be obvious what's going to happen here. Cosine pi over 2 is, of course, 0, so that's going to give us another 0. F to the 4th, or f of the 4th derivative of f of x, or f at prime of 0, or, excuse me, pi over 6. It should be pi over 6's. Gives us 81 sine of pi over 2, which we know is 1, so that's going to give us 81. All right. Now, let's put it into our Taylor series structure. F of x is equal to, what do we say the first term? It's 1. It's this f of prime pi over 6. So that's 1 plus, well, we have a 0 times x minus pi over 6. F double prime is negative 9. We have the 2 factorial underneath there. X minus pi over 6 squared plus 0 over 3 prime times x minus pi over 6 cubed. And last one, 81 over 4 factorial times x minus pi over 6 to the 4th. And so now we see when we're not centered at 0, we have to include these with our variable. So it's always the minus. If we were centered at negative pi over 2, this would read x plus pi over 2. So don't forget that. And the other thing students tend to miss too is this factorial. You see that a lot. The factorials tend to get missed because we're so in tune with our derivatives that we just forget that in our terms. So make sure you don't lose those. Now, we could probably clean this up just a little bit, get rid of those 0 terms, and we're just going to have 9 over 2 times x minus pi over 6 quantity squared. We also have another 0 here. So let's go to 81, that's over 24. 81 over 24 actually reduces to 27 over 8. X minus pi over cubed to the 4th. And you'll see this is a repeating pattern with our trigonometric functions. We're going to have the even values for our exponents with the signs. And if we had cosines, we would have the odd ones. Now, a question sometimes come up is how approximate is this? And sometimes I like to do this with trigonometric values because it's pretty easy to do. But if I were to evaluate this at, let's say, pi over 3, I would get f of pi over 3, which is now my Taylor series structure. I would get 1 plus negative 9 over 2 pi over 3 minus pi over 6 squared. And I won't take you through all the math on this. That'll be left to the student to do. But you're going to find that you're going to be about 0.019969. Now, what's the true value? Well, we can look up here, pi at f of pi over 3 is going to be sine of pi. Sine of pi is 0. So that's the number we're actually comparing against. But if I were to expand this out to include 6 terms, and let's just say this is at pi over 3, this becomes a much better approximation. And even at 8 terms, we get even closer. And so this is how I find Taylor series to be very interesting, is that the more terms that we include, which is more work, we're going to find we're going to have a better and better and better approximation as we go along. And that's the power of the Taylor series. So let's look at the Taylor series for a generic number of terms, so x to the k. In particular one, it's going to be 1 plus x, and that's an important thing because we're going to see what falls out of this. If I were to work through this, f of prime of x is going to be k, remember by the power rule, 1 plus x k minus 1. F prime of x is k times k minus 1, because that comes down and becomes k minus 2. And I can keep doing this, k minus 1, k minus 2, 1 plus x to the k minus 3. And if I keep doing this until I decide to stop, then it's going to give me k times k minus 1, k minus 2, a continued multiplication here until I get to k minus n plus 1. This is the number of terms I want to put in my Taylor series approximation. Now, if we evaluate these at 0, just like we do before, f prime, let's do the f of 0. If I put a 0 in here, I get 1 to the k, so that's just 1. If I put a 0 in here, I have my k out in front, but I have 1 to the k minus 1, which is just 1. F prime of 0, I get k and k minus 1 again. 0, so once again that's 1. And you can start to see what's happening with the pattern. It's k times k minus 1, k minus 2. Carry it on until you get to the nth derivative. And again, you will have k minus 2 multiplication k minus n plus 1. Over here, I did forget my very last term times k minus up to the k minus n. So this is what we call, and if we put this back in our structure, we're going to see that this has a very specific term or a very specific function. 1 plus k times x, k times k minus 1 over 2 factorial, x squared is k times k minus 1, k minus 2 over 3 factorial, x cubed, plus so on until we get to our last term, which is k minus 1, k minus 2, times n factorial, x to the n. Now, if you're observant, you'll notice that this is the binomial expansion. So this is called the binomial series. And it's very useful for terms for our functions that look like this, 1 plus x. It's very useful. And so it actually creates a nice, easy structure that we can quickly go through. And what we see is that every time we're going to look at our power, we're just going to subtract 1. So in this example, our k is 1/3. So now we have everything we need here. We can just go right into using our binomial series. So f of x is equal to 1. We get that one for free. 1/3 x plus 1/3. 1/3 minus 1 gives us negative 2/3. Don't forget the 1 over 2 factorial, x squared, plus, same thing, negative 2/3. Now we need to take off another 1 from that, and we get negative 5/3. And we have 1 over 3 factorial, x to the third. And just for fun, let's do one more term. So once again, 1/3, negative 2/3, negative 5/3, minus 1 again gives us negative 8/3, x to the fourth, and so on. And if we work this out, because this looks like fun, well, we get a 2, that crosses off with this. We do have a negative, so that's a minus. We have a 9, 3 times 3, which is 9, bunch of 1s in the numerator, so 1/9 squared. Let's go to the next term. This is 3 times 2, so we can cross this off and make this just a 3. We have 2 negatives, so that's a positive. We have 5 times just 1s, so that's 5. And then 1, 2, 3, 4 3s, and that gives us 81, x cubed. Here we have 3 negatives, that's 3, so that gives us a negative there. This is, and I did forget my 1 over 4 factorial. So remember that's 24. Well, we can cross that off. We have 3. So 1, 2, 3, 4, 5 3s. 243 in the denominator. And just 10 in the numerator, 5 times 2, because this 8 went away. And that gives us x to the 4th. And so on. And so that becomes the binomial series expansion for 1 plus x, the cube root of that. One more example, this time where we don't have just 1 plus x, we have 1 minus 2x. So we have to make an adjustment to how we do this. So once again, we're going to just go straight to our binomial structure. And we're going to see first that we have k is 1/2. So I have 1 plus 1/2. And now instead of just x here, it's not going to be x, it's going to be minus 2x. So we have minus 2x. Again, same thing, 1/2 minus 1 is 1 over 2, is negative 1/2. 1 over 2 factorial. And we have negative 2x squared. Plus, once again, 1/2, negative 1/2, negative 3/2, 1 over 3 factorial, minus 2x cubed. And one more term. You can see I like to do them in 4s. So now we introduce now negative 5 over 2, 1 over 4 factorial, negative 2x to the 4th power, and so on. All right, let's clean this up, and we're almost done. 1/2 times negative 2x, so that's just going to give you negative x. 1/2 times negative 1/2, that's 1/4. This is 2, so that's negative 1/8. Negative 1/8 times 4x squared, that's going to give us 1/2 x squared. 1/2, negative 1/2, negative 3/2, and this is a 6. So we can cross that out and make it a 2, and that becomes a 1. You do have a positive here. Looks that way. Yes. So now you have 1, 2, 3, 4 2s. That's an 8 in the denominator. But you also have, that is 16 in the denominator. You have a negative 8x cubed. So this actually should be a negative. So 8, 16, that gives you a 1/2 again, negative 1/2 x cubed. And then one last term to round this out. You have 24 here. Let's make that an 8 and cross off this 3. That's going to leave you with the 5 in the numerator. 1, 2, 3 negatives. So again, I have the wrong sign, so that should be negative. You have an 8, 1, 2, 3, 4. 2s, so that's 128. So let's do this. 16 times 8 times 16x to the 4th. Well, that's pretty easy. We can get rid of the 16s that way. And you get 1/8 times that 5 gives you x to the 4th. And the next term will be negative, and so on. And so that is how you do the binomial series expansion, the Maclaurin series, and the Taylor series.